Advantage. Good morning. Good morning. You can unmute and answer.
Good morning.
Okay, that's good. So this is the electronic circuits class, okay, for telecom and electrical engineering, year 2, okay. So we want to start on operational amplifiers, okay, but we're quite a few people, only about 17 people. So we'll have a brief introduction. Okay, I hope you have looked at the content which I put on Mwele. Okay, I gave you the introduction. In other words, what is expected of you. Okay, how you'll be assessed, what you expect to achieve by the end of this course, and then also, of course, a few references. So majorly we'll be using microelectronic circuits by Cedra and Smith. It is freely available. I think I put the link on Mwele. Okay. So how you'll be assessed, as already noted in the introduction, you're supposed to have a test which contributes 10%. You're supposed to have an assignment that also contributes 10%. You're supposed to have labs, those contribute 20%. And then, of course, the final exam. Okay. So we can have a number of tests and a number of assignments. Okay. Perhaps, I don't know whether you have followed the communication from the university that you may have to join. I mean, you may have to return the university in order to do your tests. Okay. So we'll have some tests also, I think, during that period. But in the meantime, we'll have tests using the Mwele platform. Okay. Now, I want to briefly give you an introduction to operation amplifiers. Here, I'm assuming that you already have the notes or the slides, and you have even looked at them. So to make it faster, we'll just highlight a few of the important things. Okay. So at this point, let me ask, are there any questions? Do you have any questions? Okay. Okay. So if you don't have questions, then perhaps we can continue. Okay. There are only a few people, but I hope that others will join as we go along. Okay. And then also another issue is that at the moment, the staff are still on strike. So I don't know what will happen next. Okay. But whenever I'll have a meeting, I'll inform you in advance. Okay. And hopefully the next time we'll have a longer period. Okay. But this is really just for the introduction. Okay. Can you see the screen? Hello?
Yes, we can see.
You can see it. Okay. So we're starting with the operational.
Yes.
Okay. That is good. We're starting with operational amplifiers. Okay. So the subtopics which we expect to cover are, of course, we'll have a short introduction. We want to look at the ideal operational amplifier, abbreviated as op amp. We want to see how it operates in the inverting configuration, the non-inverting configuration, how we can design integrators and differentiators, and then later on, look at some of the imperfections of practical op amps. These are what we call the DC imperfections, and then also the effects of finite open loop gain and bandwidth, and lastly, the large signal operational op amps. Okay, the learning objectives. By the time you finish this particular topic, you should have understood the terminal characteristics of the ideal op amp. You should also be able to analyze circuits containing op amps, resistors, inductors, capacitors. You should be able to design amplifiers using op amps. You should be able to design also more complicated or sophisticated op amp circuits, including the summing amplifiers, instrumentation amplifiers, and so on. And then we'll also look at the non-important ideal characteristics of op amps and how they affect the performance of basic op amp circuits. Okay. Introduction. Operation amplifiers have been in use for a long time. Initially, they were only used for analog computations. By analog computations, we mean addition, subtraction, okay, those kinds of operations. And initially, they were constructed from discrete components, but now the trend is towards using ICs. So you're more likely to find an op amp in the form of an IC rather than one from discrete components. So for this course, we'll be focusing on the IC op amps. Okay. Another thing is that an op amp is a popular device because of its versatility. That means we can derive very many applications using an op amp in an electronic circuit. We'll look at some, but the rest will be left to you. Okay. So, okay. That's a brief introduction. We can also note that an IC op amp is made up of a large number of components. Okay. These are really transistors, okay, resistors, and capacitors. They are connected in a rather complex way. Okay. Now, because of the complexity of the circuit and also the fact that we have not covered transistors, we are not going to look inside the op amp. What we'll do is to treat the op amp as a circuit building block and simply study its terminal characteristics, which can enable us to design applications. Okay. By terminal characteristics, we're looking at the input voltage, output voltage, input impedance, output impedance, and so on. Okay. But if you want to look inside the op amp, you can look at chapter 13 of microelectronic circuits. Okay, I think this is the 7th edition, so it will vary depending on the edition which you have. Okay. Okay, so let's start by looking at the ideal operational amplifier or op amp. Just like any other amplifier circuit or any other electronic circuit device, we must have a symbol that represents the device. Okay, so the symbol we're using here is a triangle. Now, a triangle in general is a symbol for an amplifier. Okay, if you've looked at chapter 1 of microelectronic circuits, and I encourage you to look at chapter 1 of microelectronic circuits, okay, which will give you an overview of amplifiers, the terms used, okay. When we talk about voltage gain, current gain, what do we mean? Okay, so these are things which you should review in chapter 1. Okay, now the ideal op amp is represented by a triangle, and inside the triangle we have a minus and plus. That distinguishes it from the ordinary amplifier connection. from the ordinary amplifier. Okay, so we need to know what these terminals mean. You can see that we have labeled terminals 1, 2, and 3. 1 and 2 are input terminals. Okay, specifically, 1 is the inverting input terminal. We'll see why later on. 2 is the non-inverting input terminal, and 3 is the output terminal. Okay, sorry about that. I think my network must have disconnected. Okay, but where did we stop? Where did you stop hearing? Hello? Oh my God.
Excuse me, madam.
Yes? Yes?
Excuse me, madam.
Yes, I can hear you. I can hear you. Hello?
Yes, madam. You are breaking.
Hey, sorry. I think my network is not very stable.
You're breaking.
Okay. So where did I stop? Where did you stop here? Can you hear me now? Hello? Hello?
I can hear you.
We are hearing
You're
you.
hearing me now. Okay. Where did I stop? Had I covered the terminals of the ideal op amp?
Yes.
Yes. Okay. Okay. So let me try to continue as we hope the network will not interrupt again. Okay. Yes. So as I was saying that these 3 terminals are not the only ones which are on an op amp. Okay. We need to have more terminals. You find that the IC has 8 terminals. Okay. So let's start by introducing 2 more terminals. Okay. If you look at the figure 2.2a, okay, we have introduced 2 more terminals, terminal 4 and terminal 5. Okay, terminal 4 and 5. You can see that 4 is connected to a positive supply, VCC, and 5 is connected to a negative power supply, minus VEE. These are DC power supplies. Okay, in order to get the op amp to work, you must supply it with DC power. And we'll see that for all the amplifiers which we'll use, you must supply them with DC power. Okay. Sometimes when people do their simulations in multisim, for instance, they may forget these power supplies. Okay. But these are very important. Without them, the op amp cannot work. But when we're doing our analysis, okay, for the course, you know, in the exam and so on, we don't usually include them, but we just keep them in mind that they must be there. Okay, so 4 and 5 are power supply terminals. Okay, and the positive terminal of the supply VCC is connected to terminal 4, while the negative terminal of VEE is connected to terminal 5. You do this hopefully in the labs, okay? And we'll see the importance of the power supply later on when we look at the large signal operation of the op amp, okay? The other terminals which are included are for frequency compensation, okay? We'll see that later on, and also for offset nulling, okay? offset nulling. Okay. So next we move to the circuit operation of an op amp. We always start by looking at the ideal op amp, because even the characteristics of the practical op amp are made, to be as close as possible to those of the ideal op amp. Okay. So we will be introducing a few aspects which distinguish the ideal from the practical one. Okay. So what is our ideal op amp? The ideal op amp is one that is designed to sense the difference between the input signals applied at its two input terminals. Okay. So what do we mean by sensing the difference? We have already seen that it has two terminals. So if I apply a voltage, sorry about that, the network is bad, but let me request those who have turned on their videos to turn them off, so that we try to minimize the usage of the network. Okay, so you can turn off the videos. Okay. Let me share the screen again. Please turn off your videos. Okay. So we're saying that if I apply a voltage at terminal 2, I call it V2. If I apply a voltage at terminal 1, I call it V1. Okay. These voltages are taken with respect to ground, so that we have V1 taken with respect to ground, V2 also taken with respect to ground. So what the op amp does is that it gives you an output which is the difference between the two input voltages, and then multiplies it by a number A, okay? So that the output voltage is actually A times V2 minus V1. That is the output which appears at terminal 3, okay? And we can say that V3 is equal to A times V2 minus V1, okay? So it is essentially what they call a difference amplifier, okay? Now, if we want to use the op amp in a circuit, we have to understand the way it operates, that is, its characteristics, okay? There are about 5 characteristics of the ideal op amp, okay? The first one is that the input impedance of an ideal op amp is infinite. The input impedance of an ideal op amp is infinite, okay? But of course, practically, you cannot have an infinite input impedance. So you'll find that, for instance, the 741 op amp will have an impedance of about 100,000 ohms, okay, or 1 mega ohm, okay. But for the ideal case, we'll take it to be infinite. And what is the implication of having an infinite input impedance? Okay, the implication is that the ideal op amp does not draw any input current. Okay, that is, the signal current into terminal 1 and the signal current into terminal 2 are both 0. Okay, then another, or the second characteristic is that the output impedance of an ideal op amp is 0. The output impedance of an ideal op amp is 0. Okay. Why? Because at the output, the voltage is fixed. We have A is the gain. We'll see that's referred to as the open loop gain of the op amp. A times V2 minus V1. So if V2 and V1 and A are fixed, the output will also be fixed. If we put a resistor, that is a load, at the output between terminal 3 and ground, okay, the current that will be drawn by that load will depend on the load, okay? It will not depend on the output voltage. So we can vary our load current from 0 to infinity, but the output voltage will remain constant, okay? So because of that, we say that the ideal op amp has 0 output impedance. Okay, those two characteristics are very important. Infinite input impedance and 0 output impedance. They help you to design and also to understand the different op amp circuits. Okay. Another important characteristic is that an ideal op amp has 0 common mode. Okay, so sorry about the network. Okay. We'll try to improve it with time, okay? So what I was saying is that, the ideal op amp has 0 common mode gain, okay? Or we could say infinite common mode rejection. That is, it rejects common signals such as noise. What do we mean? If V1 is equal to V2, you can see that your output V0 will become 0, okay? So in our case, we're still saying V3, voltage at terminal 3, okay? So the voltage at terminal 3 will be 0, okay? So that is what we're referring to as 0 common mode gain, okay? Or infinite common mode rejection. So that's a very important characteristic of the op amp, okay? The other important characteristic is that it has an infinite open loop gain. The gain that we denoted A earlier on is what we're referring to as an open loop gain. So later on, when we close the loop, okay, between the output and input, we'll start talking about a closed loop gain, okay? Another characteristic is that they are direct coupled or DC amplifiers, okay? That means they can work even for signals, that for DC signals up to infinite frequency. And that brings us to the last important characteristic, the fact that they have an infinite bandwidth, okay? They have an infinite bandwidth. Infinite bandwidth simply implies that they can amplify signals of any frequency with equal gain from 0 to infinite hertz, so to speak, okay? Do you have any questions? Any questions?
Yes, please.
Yes?
Could you please explain the 0 common mode gain again?
0 common mode again. Okay, who is this? Can you just identify yourself and whether you're from telecom or electrical? Okay, I didn't get that.
Nambi.
Yes?
Ranela Nambi from electrical.
From electrical. Okay. So the zero common mode.
Ranela Nambi from.
Okay, okay, thank you. Now we're saying common mode rejection. Common mode simply implies that the signals are the same. Okay, that means V1 is equal to V2. Okay, so if we apply a signal, we say maybe V1 is 1 volt and V2 is also 1 volt. Okay, what will the output be? What is V3? Okay, what is V3?
It would be 0.
It will be
It
0.
would be 0.
Okay, so that is what we're saying, that it rejects common signals. Okay, and noise will usually appear at both terminals with the same amplitude, same frequency, and so on. Okay, so in that way, such a signal is rejected, and that is what we're calling common mode rejection. Okay, and later on, when you do analog electronics, you will define this term better, the infinite common mode rejection. Okay, so here it's zero common mode gain because the gain is 0. What is gain? It's simply the ratio of output voltage to input voltage. Okay, alternatively, you can say infinite common mode rejection. Then you'd need to define this term, infinite common mode rejection. That you will do in 3rd year when you do analog electronics. Okay. So are there any other questions? No. Somebody called Kiamufumba Dennis. Kiamufumba Dennis. He has been trying to join, but I don't know. It appears he's not joining. Someone is drawing on the screen. Please stop that. Okay. Namukwaya. Okay, please don't draw on the screen. Okay. Yes. So when we take these characteristics and put them into what we call an equivalent circuit, okay, we represent them as shown in figure 2.3. Okay. So here you can see that the input current into the inverting input terminal is 0. The input current into the non-inverting input terminal is also 0 because the input impedance between these two terminals is infinite. Okay. Ideally, it is infinite, but practically, it will be some large value. Okay. Then we have a dependent source connected to the output. The dependent source is simply telling us that the output of your amplifier is A times the difference between V2 and V1. That is what it's telling us. Okay. Okay. So next we move to look at the inverting configuration of an operational amplifier. Okay. As we mentioned, the open loop gain A is usually very large. And for an ideal op amp, it is actually infinite. Okay. Of what use would such an amplifier be to a designer? Okay. Or to, yeah, definitely to a designer, okay, of an electronic circuit. Okay. If you have an infinite gain, that means you cannot control the output of your circuit, okay? And practically, your output will not go to infinity. It will be limited by the power supplies. So if you're feeding your op amp with plus minus 15 volts, then your output will always be either at plus 15 or minus 15 volts, okay? At plus or minus 15 volts. So what do we do if we want to design circuits that we can easily control, okay? So of course, there are also circuits that use the op amp in the open loop mode, okay? These include the comparator circuit. You can write this down somewhere. I'll possibly give it to you even in an assignment. The comparator circuit, which compares, okay? Okay. So you can write down somewhere the comparator circuit, okay, which compares two signals, okay, and gives you an output. That one is a digital circuit. But now we want to look at the analog circuits that we can derive using an op amp, okay? So what do? We close the loop between the output and input. This simply implies that we provide a connection between the output and the input, okay? If you see the figure, we have introduced two things, okay? We've introduced two things. We have resistor R1, and then we also have resistor R2, okay? Resistor R2 is connected between terminals 1 and 3, okay? Terminal 1 is an input terminal, while terminal 3 is an output terminal, okay? So what we have done is referred to as applying feedback. We have applied feedback to our circuit, okay? We've applied feedback to our circuit, and we want to see how this circuit will operate, okay? Some people are drawing on the screen. I don't know. Please, you stop that. Since you're university students, I don't expect that you behave like like your brothers or sisters in lower classes. So let's not be excited about this. And I can imagine that you've used this platform before, isn't it? Yes, you have. Okay. Yes, so going back to what we are saying, that if we apply feedback, okay, where feedback is simply a connection between the input and output of an amplifier, okay, between the input and output of an amplifier, then we are able to improve the accuracy and stability of the amplifier. We'll see later on what we mean by accuracy. And stability is something that comes later on. It's, I think, the last topic, okay? So we note that there are two basic circuit configurations that employ an op amp and two resistors. One is the inverting configuration, and the other is the non-inverting configuration, okay? So what we are looking at the moment is the inverting configuration, okay? And we mentioned that the inverting configuration has a resistor R1 and R2, with R2 in the feedback loop that is connecting between input and output, okay? We can also say that resistor R2 applies negative feedback. So those who have turned on their videos are disorganizing my network, okay? Those who have turned on their videos are disorganizing my network. Okay. Okay. So we've already mentioned that if you apply R2 between terminals 1 and 3, you apply feedback, and it's negative feedback. Later on, we'll understand why. Okay. But simply put, it's because it's connected the inverting input terminal, okay, where we're subtracting. Okay, there's some kind of subtraction there. We talk about negative feedback. But if R2 were connected between terminals 3 and 2, we would talk about positive feedback. Okay, but what we use most of the time in amplifiers is negative feedback because it is more stable than positive feedback. Positive feedback can easily cause oscillations. Okay. Yes. Then the other thing to note in this circuit, okay, is that we have grounded terminal 2. That is the non-inverting input terminal. And our output V0 is taken at terminal 3. Okay. That is between 3 and ground. Okay. Yes, so if you have a load, you must connect it between terminal 3 and ground. For your case, the load can be a simple resistor. It can be a light emitting diode. It can also be another amplifier, okay? Another op-amp amplifier, okay? So let's look at the inverting configuration. What do we want to do with it, okay? Most of the time in this course, you will be required to determine some gain, okay? Whether it's a voltage gain, current gain, power gain, okay? That is what we're talking about in this course, okay? Of course, with the exception of diodes, which are passive devices, okay? So you will be required to determine the gains, okay? And now that we have closed the loop in our amplifier circuit, we want to determine what we're referring to as the closed loop gain of the amplifier. We define the closed loop gain as the ratio V0 to Vi, okay? We define it as a ratio output voltage to input voltage. So this is basically a voltage gain, okay? Then in order to do the analysis, we need to assume that the op-amp is ideal. So we take on all those characteristics: an infinite open loop gain A, an infinite input impedance, and a zero output impedance, okay? So when we assume that the gain A is very large, ideally infinite, okay? We assume that. If we assume that the circuit is working and producing a finite output voltage at terminal 3, then the voltage between the op-amp input terminals should be negligibly small and ideally 0, okay? Specifically, if we call the output voltage V0, then by definition, Vi, okay, just a moment, call the output voltage V0, then by definition, this should be V2 minus V1, okay? So what are we saying? We know that output voltage V0 is equal to A times V2 minus V1, okay? But if we look at our circuit, okay, what is the voltage at 2? The voltage at 2 is, hello? What is the voltage at 2? Terminal 2?
0.
Zero.
Okay. So if V2 is 0, okay, we're going to get to that anyhow, okay? So we can rewrite our expression. We know that V0 is equal to A times V2 minus V1. If I make the difference voltage between V2 and V1 equal to V naught over A, okay? When I let A tend to infinity, okay, then V naught over A will tend to 0, okay? When I write my expression in that form, and then I say, but A tends to infinity, that means V naught over A will tend to 0, which will imply that V2 minus V1 is equal to 0. That brings us to a very important result, okay? If V2 minus V1 is equal to 0, it implies that V2 is equal to V1, or that V1 is equal to V2, okay? And this is what we refer to as the virtual short circuit, okay? So coming from the characteristics, okay? Coming from the characteristics, we have seen that the voltage V1 is equal to V2, okay? The characteristics impose that conclusion, okay? That V1 must always be equal to V2. So we can say that because the gain A approaches infinity, the voltage V1 approaches and ideally equals V2. So we can talk about the two input terminals tracking each other in potential, or we can say that there exists a virtual short circuit between the two input terminals, okay? Virtual short circuit means that whatever voltage is at terminal 2 will automatically appear at terminal 1 because of the infinite gain A, okay? It is virtual because it is not a physical connection. We know that between the two input terminals, there's an infinite. Okay, sorry about that. Okay, so we're talking about the virtual short circuit. Okay, and we're saying that a virtual short circuit appears between terminals 1 and 2. Okay, so the voltage at one terminal will determine the voltage at the other terminal. Okay, that comes from the characteristics of the op amp. Okay, not the external circuit which we have applied. Okay, so continuing, so we can put all this information in a diagram, okay, showing us the analysis, okay. So we have already said no current enters the input terminals 1 and 2. Between 2 and 1, there's a virtual short circuit, okay. So what does that imply? It implies
Excuse me,
that,
madam.
yes? Yes? I can hear you. Hello? Okay, somebody said excuse me and then went off. Okay. Hello? Okay. So we were saying that, okay, that the voltage at terminal 1 will follow the voltage at terminal 2 because of the virtual short circuit. Okay, since terminal 2 is at 0 volts, okay, since terminal 2 is at 0 volts, it implies that V1 will also be at 0 volts. Okay, is that okay?
Excuse me, madam.
Yes. Yes.